channel Nature and Science.
Hello students, my name is TJ Medi. I am your science mentor. In this video, we are going to discuss about electrostatic potential energy and potential. Now, what is potential energy? If any object is under the influence of a continuous force, it possesses potential energy. This principle is also applicable for stars. This video is made with utmost care to boost your knowledge on this topic. At the end of this video, some important terms have been discussed, so I insist you to watch this video till the end. So let's begin. Let us consider a scenario where we have two surges. One is plus capital Q, another is plus small q at infinity. Now the amount of surge present in plus capital Q is much more than that of plus small q. Hence, plus capital Q is considered as the source surge and plus small q is considered as the test surge. Later we'll discuss the significance of taking test surge in this case. Now we have a space where A and B are 2 points separated by distance smaller. This space is empty, that is, there is no electric field in this space. Hence, when we bring the source surge, that is plus capital Q, from infinity to the point A, we do not have to do any work done. This point is very important to understand. Now, as the source surge reaches the point A, the whole space is filled with radially outward electric field. Now, any surge that enters into this space will experience either attractive or repulsive force in nature. Hence, the test surge, as it moves towards the source surge, will experience Coulomb's repulsive force. Here we are going to bring the test surge from infinity to the point B. Now we have two options to bring the test surge. One is by using an external force that is greater than the Coulomb's repulsive force. Another is using an external force that is equal to Coulomb's repulsive force. When we use an external force that is greater than Coulomb's repulsive force, the net force acting on this test surge will be positive, and hence this test surge will be accelerated towards the source surge plus capital Q. But the problem here is that in doing so, it will be difficult for us to find out the magnitude of the external force. Now, when we use an external force that is equal to Coulomb's repulsive force, the net force acting on this test surge will be 0. Hence, this test surge will move without accelerations, that means with uniform speed, towards the source surge plus capital Q. Now, the amount of work done in bringing the test surge from infinity to a point B can be determined easily, because in this case, the external force becomes equal to Coulomb's repulsive force. Now let us consider a point P which is at a distance x from the source surge, and there is a length element dx along the directions of motion of the test surge. As the test surge reaches the positions P, it will experience two equal and opposite force. One is the external force which acts along the directions of motion of the test surge. Another is Coulomb's repulsive force. Here, Fexx is the external force acting on this test surge at a distance x from the source surge. Similarly, Fcx is the Coulomb's repulsive force acting on the test surge at a distance x from the source surge. Both are equal in magnitude but opposite in direction. But Coulomb's repulsive force increases as the distance between the source surge and the test surge decreases. So it is a variable force. So to find the work done, we will use integral method. Now this length element is infinitesimally small, so we consider that the Coulomb's repulsive force for this displacement dx remains same. Now we can find the work done by the external agency in displacing the test cells by the small distance dx. So it is the dot product of the Coulomb's force and the displacement. Here we have seen that the directions of displacement and the Coulomb's force are opposite in directions. So the angle between these two directions is 180 degree. So the dot product of Coulomb's repulsive force and the length element becomes equal to minus Fc x dx. Now putting the value of Coulomb's force, which is capital K into capital Q into small q divided by x square. In this equation, we get the work done dW for the small displacement dx is equal to minus K into capital Q into small q divided by x square into dx. Now we are in a positions to find the total work done in displacing the test cells from infinity to the positions B, which is at a distance r from the source cells. Now the work done by the external agency in bringing the test cells from infinity to the point B is capital W is equal to integration from 0 to W dW. We have already determined the value of dW as capital K into capital Q into small q divided by x square dx. Now the limit here is infinity to r because the test cells is brought from infinity to the point B, which is at a distance r from the source cells. Now the value of integration dx by x square is minus 1 by x, and here capital K, capital Q, small q all are constant, so they are kept outside of the integrations. Now putting upper limit r and lower limit infinity in the result of integration dx by x square, that is minus 1 by x, we get minus 1 by r, r is the upper limit, minus 1 by infinity, infinity is the lower limit. Here 1 by infinity is 0, so whole these terms becomes 1 by 4 pi epsilon capital Q into small q divided by r. Here 1 by 4 pi epsilon is the value of capital K, and epsilon is the permittivity of the medium where the two surges are kept. Now medium means it may be glass, it may be distilled water, it may be paper. So depending upon the nature of the medium, the value of epsilon varies. Now the external agency in expense of energy has to do the work done in bringing the test cells from infinity to the positions B, which is at a distance r from the source cells. We know energy can neither be created nor destroyed. So the energy which is spent by the external agency will be stored in the test cells, which is at a distance smaller from the source cells, as its potential energy. So the work done W is stored in the test cells as its potential energy, which is equal to 1 by 4 pi epsilon into capital Q into small q divided by r. This is the standard expression of the potential energy stored in the charge small q at a distance smaller from the source cells capital Q. But when we take the medium air or vacuum, then the permittivity epsilon becomes equal to epsilon naught. So the potential energy will take this form, that means 1 by 4 pi epsilon naught into capital Q into small q divided by R. Now, what is permittivity? We will discuss it in a different video, but to understand simply, we have to take it as the measure of field lines which is allowed by a medium to go inside of it. Again, we can express potential energy as the product of the Coulomb force and the distance of separations between the source charge and the test charge. Here, in this term, both numerator and denominator is multiplied by smaller, so we get 1 by 4 pi epsilon capital Q into small q divided by R square into R. Now 1 by 4 pi epsilon capital Q into small q divided by R square is nothing but the Coulomb's force experienced by the test charge at a distance smaller from the source charge. Therefore, Coulomb's force can be written as the potential energy by the separations, by the distance of separations between the source charge and test charge. Therefore, Coulomb force can be defined as the potential energy per unit length. Let us return back to this scene again. The potential energy stored in this plus small q charge is given by capital U bracket R, which is equal to 1 by 4 pi epsilon capital Q into small q divided by R. Here the quantity 1 by 4 pi epsilon capital Q by small r can be denoted by another term capital V bracket R. So this term capital V bracket R, which is equal to 1 by 4 pi epsilon capital Q by small r, is defined as the electrostatic potential at the positions B, which is at a distance smaller from the source charge. Here we have to understand a very important point. This potential energy is associated with the charge, but potential, electrostatic potential, is associated with the position. That means potential energy is charge specific and potential is position specific. From this equation we can write electrostatic potential is equal to electrostatic potential energy divided by the charge which is present at a distance smaller from the source charge, and this can be defined as the potential energy stored in 1 unit positive charge. Hence, in books, the definition of electrostatic potential is given by the amount of work done in bringing a unit positive charge from infinity to a distance smaller from the source charge. Before I wrap up this video, let us discuss some important points. One is the test charge. Now, what is test charge? The concept of test charge comes when you compare two or more charges. Here we have two charges. One is plus capital Q, another is plus small q. And we have considered that the magnitude of plus capital Q is much more than plus small q. In such a scenario, the electrostatic force of repulsion applied by plus small q cannot displace plus capital Q. Or we can say that the presence of plus small q near plus capital Q cannot alter the electric field of plus capital Q. In such a scenario, the plus small q, which has very less magnitude in comparison to plus capital Q, is called the test charge. Now the second point is that we keep the two charges, that means plus capital Q and plus small q, initially at infinity. What is the reasons behind that? The electric field is zero at infinity. So is the electrostatic force. Hence, it helps us to find the exact work done in displacing the test charge from infinity to near the source charge, because in this case the electrostatic force starts from zero to its maximum value. Now the third point is that in displacing the test cells from infinity to near the source cells, we apply the external force that is equal to Coulomb's repulsive force but not greater than Coulomb's repulsive force. What is the reasons behind that? If the external force applied is greater than Coulomb's repulsive force, then it will be difficult for us to find the value of the external force which is used to determine the work done in displacing the test source from infinity to near the source source. Again, if the external force is greater than Coulomb's repulsive force, then the net force acting on the test source will not be zero. In this case, the test source will be accelerated towards the source source. But we know one thing, that any such particle under accelerations emits electromagnetic radiations. So some part of the energy of the external agency will be converted into electromagnetic radiations. Hence the total work done will not be converted into potential energy. For these reasons, we cannot apply an external force greater than Coulomb's repulsive force. So students, I hope you have earned some knowledge from this video, and I will be happy to see you again in my next video. So till then, goodbye and take care.